Hello, pre-calc students. This is Mr. Beck. I'm here to talk today about lines, circles, and beginning to work with functions. If you remember what we did in 1.1 and 1.2, we talked about the distance and midpoint formulas. We did a bunch of work with individual skills. We also spent some time working through some problem-solving approaches to problems. 1.3, we're going to talk a lot about lines, and we begin by saying, what do you remember about lines? Well, a vertical line has the form x equals a number. In this case, I'm just going to say c is any number, so x equals c is my vertical line. Y equals 0 is an example of a horizontal line, or y equals c is going to be a general case of any horizontal line. We know slope is rise over run. Rise over run, we consider that delta y over delta x, where delta is the Greek letter for change. You see that a lot in chemistry, delta T for change in temperature. We measure rise by saying the distance between our y values. We measure run by the distance between our x values. Perpendicular slopes, we know the perpendicular slopes are opposite reciprocals of each other. So if your slope is a over b, your perpendicular is negative b over a. Now, one of the properties of perpendicular slopes is when you multiply them together, you get negative 1. This is something that's good to mention now, but has a lot of implications when we start talking about vectors in the future. So, we have a couple different forms of a line. The main form that is kind of more of an irrational form is ax plus by equals c. Something specific about a, b, and c. A, b, and c are supposed to be integers. Now, some textbooks require that a is a positive number. Ours, I don't think mentions one specifically, but it's kind of like nicer just if you're beginning your equation with a positive number. Slope-intercept form, everybody's favorite, y equals mx plus b. It's the most familiar to people. In real life context, if we have a graph that says, hey, we're charging so much, and then per hour we charge an additional amount as a linear function. In real life, we work in quadrant 1, so slope-intercept form tends to work really well for quadrant 1 real life issues. Point-slope form is my personal favorite. Point-slope form, what we do with it is, we know that we need to have a point and a slope to make a line anyway. So with point-slope form, it's a nice, easy, let's set it up and drop all the information in, plug in your slope, plug in your point, and you're done. Now, if you need an equational line, you're done. If you need to do anything with it, then you can manipulate your equation further. So one of the also points I like to make with point slope form is, you remember from algebra 2, where if you take the equation y equals x, the slope is the dilation of that parent function y equals x, and then the x1 and the y1 are going to be your translation. So when you talk about dilations, reflections, and transformations, or translations, and transformations overall, then we now know that point slope form is of that same kind of mentality. A couple skill problems. Find the equation line with slope 1/2 and the y-intercept of 3. So as you're taking a look at this, the big thing is, what piece of information can you pull from the problem? It's pretty straightforward. Your slope is 1/2 and your y-intercept is 3. Which form seems to make the most sense? Point slope form, which is why we're using it right here. What's the slope of the line? 8x minus 3y equals 1. My thought behind this is, in order for me to find the slope, probably putting it in slope-intercept form is going to be beneficial, which is what I did here. Now that I know slope-intercept form, I can identify that the slope is the number or the coefficient in front of the x. So the slope is 8/3. This level 2 problem, find the equation of line with the given characteristics. I told you point slope form is a very legitimate form. Slope at 2/3, we plug in right here. Point 4,6, we plug in right here. And we have an answer. I have a lot of students who really don't like that as an answer, but it still is a legitimate answer despite being in a form that students tend to not like. Now, if I want to do anything with it, I could solve for y. So if you gave me this equation as y equals 2/3 x, let's see, that's minus 8/3, negative 8/3 plus 6 to negative 8/3 plus 18/3 is 10/3. So if you gave me this answer as y equals 2/3 x plus 10/3, yes, we're correct. But if you heard me talk through that process, there's more work involved, there's fractional work, and the question is, why do you want to do all that fractional work when you have a legitimate form of a line? So with that said, now can you find the equation line with these given characteristics? I see that I have two distinct points I need to know a point, one of those points, and the slope in order for me to come up with the equation of the line. So the slope is what I'm missing. To find the slope, rise over run, change in y over change in x. And then I have two different answers that I could choose. Honestly, if I really wanted to do the slope-intercept form, I could as well. What's nice about the slope-intercept form is it is our common form, so both answers should go to that slope-intercept form. But do we need to do that? And the question is, no, we don't. We can leave the answer just as it is. So I'm going to. First level 3 problem, we have our slope through this point, and if you see, I've already set up, I can already set up the -6 and the -1 if I give them the point that this line goes through. What I'm missing then is the slope, perpendicular. Well, how do I find perpendicular? First, I find the slope of 7/2 and then make it perpendicular by opposite reciprocal. This problem right here, this is not done very well algebraically. So if you said y equals 0, x plus 9, because the slope of a horizontal line is 0, you go perpendicular, the perpendicular is 1 over 0, negative 1 over 0, which neither one of those really make too much sense. So it's a lot easier to go graphical approach on this, where I know the perpendicular to a horizontal line is a vertical line. And if you remember from what we set up here, that a vertical line is x equals. And since we have x equals, and we know that this is the point that it goes through, x equals 8. And by the way, that's that point right there. Find the line perpendicular to the line through those 2 points and through that fractional point. Now, I'm supposed to find all 3 forms. So my very first step that you can see that I did right here was to find the slope that goes through those 2 points. So the slope through these 2 points is -10/7, and I can come up with a perpendicular slope from that, the opposite reciprocal. Point slope form is the natural beginning. And since point slope form is the natural beginning, what we do with that is then we can go ahead and distribute through and solve for y to get it into our slope-intercept form. Now that we have our slope-intercept form, what we could do is we could bring the x's and y's together on the same side and then multiply by the LCD, which I have right there. Our LCD is -60, so that we can get it into our standard form. So that's a lot of extensive work with lines. I know a lot of students tend to be a little bit nervous about working with fractions, but at the same time, part of what I do in the pre-calculus is I'm trying to rebuild some of those fractional skills in preparation for what we're going to do next semester. Next semester, we are going to be talking trigonometry, and trigonometry is all about fractions. So the more fractional work we can build up now, just to kind of re-hit some of those skills so they're not entirely lost, the more work we could do now, the better off we're going to be, the stronger math students are going to be. 1.4, circles. The definition of a circle from geometry is a set of all points x, y equidistant from the center. So the moment I say equidistant, suddenly to me that tells me I'm going to be using the distance formula. So from the distance formula, my distance, if we draw it over here on this graph, my distance that I have here, we call the radius. And the points that I have here, x, y, and then the center of h comma k, allow me to use the distance formula to say my distance or radius is going to be, let's change colors on this, it's going to be x2 minus x1, which is how I get the x minus h squared, and then plus y2 minus y1, which is how I get the y minus k squared. And so from that, if I square both sides, then I get the equation of a circle. So what's really cool is by definition geometrically, the circle is a collection of all the points equidistant. Algebraically, we can see that the equation does come from the distance formula. And I'm going to pause for a moment because my iPad is frozen. All right, now that my iPad is unfrozen, let's continue on. So our standard form of a circle, we see here as what we came up with from the distance formula, the x minus h squared plus y minus k squared. And then the standard form, as I said, comes from that equation of the circle. The general form is what happens when we take the standard form and we multiply it out. So if we multiply it out, we get x squared plus y squared plus ax plus by plus c equals 0. That a, that b, and that c really just represent whatever coefficients come out of the multiplication. Now, our next question is, what happens if we have general form of a circle and we want to go back to standard form? We use a process of completing the square. And what you can see here with this process of completing the square, we're going to take this middle term b and we're going to divide it by 2 and square it, and that's how we complete the square. So the idea comes from if we want to take the expression that I have over here. So this expression, if I want to factor it, I will say what multiplies to give me 25 and adds to give me 10. That would be 5 and 5. So that's x plus 5 times x plus 5. Looking backwards, we see that, okay, those 5, or that 5 comes from half of the 10 squared. So x squared minus 18x, half of negative 18 squared is 81. Half of 9 is 9 halves. Let me go ahead and write this down. 9 halves squared, it's much easier to do that as a fraction to say 81 over 4. So now level 1 problem, given that equation, and this equation in standard form allows us to find the center and the radius very, very efficiently. So the center, -3, +5, and then the radius would be, what's the square root of 49, which is 7. Second question, find the equation of the circle in standard form with that center. Well, standard form, x minus h squared plus y minus k squared equals r squared. And that information, again, comes from up here. Our level 2 problem, we're going to do some more work fractionally. So the coefficient, what I first did on this problem was I brought my x squared and my x together first, then the y squared and the y, and then I have it set up in completing the square. So I will take this 1, which is the coefficient in front of the x. 1/2 squared is 1/4. Again, 1/2 squared is 1/4. Don't forget, add to both sides to get this form. And this form shows us our center is going to be -1/2, -1/2 with a radius of 1. Now for part B, find the equation of the circle below in general form with the given endpoints of the diameter. So I need general form, and it occurs to me right now I have standard form, not general form. What I first did was I took this segment and found the midpoint, which is 4,3, and I know a lot of students can find that on their own. And then set up my standard form. Now let's take it to general form. X squared minus 8x plus 16 plus y squared minus 6y plus 9 equals 25. And if I bring all the terms together into the general form, x squared plus y squared minus 8x minus 6y, that ends up being plus 0 equals 0. So my equation in general form is right here. The level 3 problem, what you should see and notice, first of all, there's a 3 coefficient in front of both of those. Something that we could do, if it's a circle, both those numbers have to be the same, so we could divide it out. We could think that I divided everything by 3. Now, after I divided by 3, complete the square like I did before. Half of -8 squared, half of 4 squared. Add the same thing to both sides, so plus 16 plus 4, and I get that standard form of a circle, which tells me the center and the radius. And that center and the radius can tell me these 5 points. Now, the center is not really on the circle, but it helps us identify that circle. So from here, we also need to find the exact intercepts. So there's a little bit of skill review that we are doing here. That skill review that we have is, let's go ahead and plug in 0 for y to find the x-intercept, plug in 0 for x to find the y-intercept. The nice thing is we end up with some symmetry where, let's focus on the y-intercept. If I take -2, which is that y value, plus and minus the exact same number, I'll get that symmetry. And the same thing would happen y. We start off with where the center is, plus that value, and minus that value. For part B, find the equation of the circle with the given center, and then with that given center, we are going to find it tangent to the line x equals 1. Now, this is a unique style problem at first when students look at it. What does it mean to be tangent to a line? Tangent to the line, a circle is tangent where it intersects at only one spot, which is going to be right there. So by drawing this out, it allows us to see that if my point is -3, 1, this is x equals 1, the line connecting it, or the radius connecting it, is 4. And from that, we can set up that equation. Now notice how I don't have a given equation, or I don't say like put it in this form. So this is one of the two answers that I could use, and then the other answer would be the form as well. I prefer this one just because it's a lot easier to plug in the coordinate -3, 1 with a radius of 4. Example number 4 is doing roughly the same thing, drawing it out. -2, 3 roughly is right here. Tangent to the line y equals 2. That tells me the distance in between is 5. So since I have my center, I can put here, and that distance of 5, then I can set up my standard form. But this problem also says, let's take it to general form. General form of the circle is going to give me this one right here. For part B, what I love about this problem is the geometric aspect. First thing is we do have the radius of 16, or sorry, the r squared of 16, which tells us the radius is 4. If I double that, I get 8. Now the question is, how do we come up with the area of the square? In order to come up with the area of the square, I need to know what is the side of my square. So algebraically, this is the approach where if we know each side is x, so let me go ahead and write that each side is x. So we have x squared plus x squared equals 8 squared, and we can solve for x right here. You could also do this geometrically if you remember that if you take the hypotenuse of a 45, 45, 90 triangle and divide it by the leg, or divide by the square root of 2, we're going to get the leg. So 8 divided by the square root of 2 is 4 square root of 2, which, by the way, is the square root of 32. Which one of these might have the graph shown? So if you look at the first 4 problems, they're really quick to look at to say, which ones can and which ones can't. So first thing is, if you notice, this center is 2, 0, which would be right here. So that obviously does not work. And what I like about this is this helps us identify what doesn't work, not just what does work. We tend to get so used to saying what does happen that we don't always say what doesn't happen. And what doesn't happen tends to be kind of a stronger approach to thinking through these problems. So if you see on the second one, I'm going to say okay on this. What I don't like about, or what works is our center -2, 0. That means that -1, 0 is right here. And I'm saying okay because you could argue for, you can argue against, but I feel like our radius should only be about, really a radius less than 1. If you just look at these 4 problems, which is what we did in class, that would be their best option. This one has a center which is on the y-axis, not the x-axis. And then this one has a center, but this radius, that center with the radius of 2 would put us at this point on the origin. That's why I'm going to say that this one definitely does not work. For number 5, if I put it from its general form to standard form, I would say this is going to be our best bet. -5, 0 with a radius of 3. I would say this is our best bet. For number 6, our center is -5, 1. Nope, definitely not. Number 7, this one's kind of tricky that at first glance it looks like -9/2, 0 looks like a legitimate center, but this radius of 41/4, so that radius of 41/4 gives me too great of a radius in order for us to be able to have that legitimately work. And then number 8, no, we don't have. This is a positive x-axis, or positive x, not a negative x, so it's not going to work. 2.1, what we did in class, we just did a brief overview of 2.1. We're going to be talking about these definitions. You can look them up in your book. We'll talk about them tomorrow. That's the first thing we're going to be doing on our next day. But the ideas that we want to get across is, does this equation represent a function? If we know that that's a circle, we know that that's not going to be a function because a function cannot intersect, like with the vertical line test, it cannot intersect our graph twice. Algebraically, we see that by saying, let's choose a specific x value. The fact that we have two distinct y values means that we don't have a function. And that's the difference between a relation and a function. A relation just groups those two numbers together, or sometimes three, or sometimes more. But the function has each input yielding a unique output. So that's a big key thing that we're looking for as a function. Domain and range, most students tend to do really well with this. Domain are going to be your input values, range are going to be your output values. If you notice, I put these in numerical order, which is kind of common practice. Is the relation a function? The issue that we're having here is this input of 0.86 gets mapped to two different outputs, which means it's not a function because this input should only have one distinct output. Is there a way to look at an equation to determine if it makes a function? Your hint is if you have a y squared or an absolute value of y. Those are what we call even functions, which we're going to get into towards the end of, or really in this chapter. But if you have even exponents or the absolute value, then you know that you're going to have not a function. Big thing about functions, our purpose is to take the input, provide the unique output, like we said. This is usually done when we have a rule in explicit form. Explicit form usually means we solve for y. So explicit is solving for y because now we have y explicitly dependent upon x. But we will write this as f to really symbolize that this is a function. So this function here, y equals x cubed plus y squared, we will write it as f of x. Now, the reason why these are x's here, though, is because that x is your input. That's your independent variable. If your independent variable was an x, suppose it's t, then we could write it as f of t equals t cubed plus t squared. If your input is a number, you could plug in that number. And usually when we plug in that number, we will simplify it if we can. So f of 3 does equal 36. Now, by having this notation, it does give us a few benefits. The first benefit is it tells us that we are legitimately working with a function. So 3 is only mapped to 36. 3 cannot be mapped to any other number. If the input's 3, the output is 36, like I just mentioned, followed by the coordinate 3, 36 lies on the graph of y equals x cubed plus x squared. Now, all of these are going to be just a lot of problems involving this, or the concept of how do you work with functions. So for one here, I plug in 3. So 3 is my input. I can simplify all of this to -2. Problem 2, then negative x is going to be our input. And since negative x is our input, then I'm going to substitute negative x in place for x, and then simplify the expression. This third case, I'm going to take the opposite, and we really should read it as the opposite of f of x. This being the opposite of f of x, what we're going to do with that is we're going to take the opposite of whatever the expression f of x is and simplify. Just kind of as a heads up, what we're going to do in 2.3 is we're going to compare these two answers to see which one actually works. Number 4, f of 2x plus 4, that means we plug the expression 2x plus 4 in for x right here. Remember I said whatever the input is, it replaces the x. In this case, the input is an actual expression. So then simplify your result. Number 5 is something very, very important that you're going to see next year in calculus. This is called the difference quotient. I know I didn't mention that in class. I am going to mention it, and we're going to talk a little bit more about it. But this difference quotient represents slope. And as I said, we're going to talk about it. For what you are going to do is you are going to take this expression, plug in your x plus h, subtract the original function, and then simplify what that results. So this is -2x, -2h, and then plus 4, which is going to cancel out with this. This becomes a positive 2x, and where students forget is this will be a -4. So what happens is all of your non-h terms cancel, and then you're left with the -2h over h, which is -2. And then this, hopefully you guys recognize, is also slope. y2 minus y1 over x2 minus x1, which simplifies to -2. Part B does the exact same thing. I don't feel like there's anything specific I need to mention. that is, 2 over the top. One of the things I will note is I told you that this difference quotient is related to slope. So the difference quotient is related to slope. And number 6 here is also related to slope. If I just realized that number 6 isn't, I didn't finish the problem. F of 2 minus f of 0 over 2 minus 0 is going to be 4 minus f of 0 is 1 over 2 minus 1. 2 minus 1 is, or 2 minus 0 is 2, so that gives me 3 halves. I am not really surprised by that 3 halves because 3 halves is the slope right here, which does come out of the difference quotient, which also goes back to slope. So this is all about slope. This expression, a little bit more challenging only because we have to plug in x plus h, which x plus h squared. Please keep in mind that x plus h squared is x squared plus 2xh plus h squared. And that is where, let me go ahead and change colors on this. This, when multiplied by 3, is where I got that expression. And then you subtract and simplify. For part B, a little bit increased difficulty. Please know that whatever we plug in, we're going to have to plug in not just once, but plug in twice. So, and then this negative f of x is going to be the opposite of that expression. So I just changed the signs on that. Trying to see if there's anything distinctly different about this problem that I should call out, and I'm really not seeing anything. So for number 3, again, plug in everything. What I'm going to say is, as of right now, I'm just going to leave this expression as it is. As we get next year, we're going to talk about simplifying that, rationalizing the numerator, which is weird, rationalizing the numerator by multiplying by the conjugate. And then for part B, I have that work down here. And for right now, again, when we do the difference quotient, I just said leave this for now because that kind of algebraic approach, I'd like to work through it with you, but we're going to see more of the work with fractional expressions over time. So I know I jumped through the last problems a little bit faster just because they are a little bit more rote, a little bit more mechanical. If you have any questions, as always, so please let me know if you have any questions and have an amazing day.